Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson number 6 on limits involving infinity. Yesterday we had a lesson called Infinity Makes My Head Hurt. Today we're going to be directly working with the idea of limits that involve infinity, especially in the context of infinity representing quantities that grow without bound. Either x is growing without bound or the output to the function is growing without bound. So, let's jump right into it. Alright, exercise 1 says consider the function f of x equals 1 divided by x, the simplest of all rational functions. Using your calculator, quickly fill in the two tables shown below to investigate the behavior of y equals f of x as x gets very large and very small. Alright, I'd like to actually show you kind of a cool calculator technique right now that you may never have done using tables before. So let me open up the TI-84 Plus. Alright, so I'm going to show you how to fill in a table when the x values aren't spaced equally. Alright, so let's hit y equals. I'm going to clear out any equations I have in y1, y2, etc. Please do the same. Alright, and now obviously I'm just going to put 1 divided by x in for my y1. Alright, now I'm going to go into my table. So let's go into our table setup. I'm going to go into my table setup. Let's do that. Now, unlike when we were investigating limits where we were getting infinitesimally close to a particular value of x, what I want to do now is I want to not worry about where the table is going to start. I'm not going to worry about what my delta table is. In fact, I'm going to go down to this line right here where it asks independent, and you notice how it says automatic, right? What I'm going to do is I'm going to change that to ask. So I have to go over and hit return on ask. Notice it's highlighted now. I'm not going to do anything with the dependent variable. Okay, I'm just going to leave that the way it is. Okay, it's going to ask me now what the input variables are. So let's go into the table and see what it looks like. Look at that. It's a blank table. There's nothing there. What it's waiting for is for me to give it an x value. So I'm going to give it the x value, negative 1,000. Enter. And there's my y value, negative 0.001. Now, unlike a normal table which gets spaced evenly, now I'm going to just have to type in x equals negative 100. And it gives me negative 0.01. Finally, I'm going to put in negative 10. I'm going to have you do the rest on your own. And it gives me negative 0.1. So what I'd like you to do is fill in the rest of the table. All right? I'm going to actually get rid of the TI-84 Plus right now. It's the only reason I needed it. And I'm not going to do absolutely every one of these because I just wanted to show you that technique, okay? So, bye-bye. All right, take a moment and fill in the rest. All right, let's go through it. Well, I've got negative 1 when I put in negative 1. I've got negative 10. Here I've got negative 100. Here I've got negative 1,000. Over here, maybe I'll go in a different color right now just to really illustrate this. I've got 1,000. Here I've got 100. Here I've got 10. Here I've got 1. Here I've got 1/10. 1/100th. Whoops, just made a mistake there. My apologies. 1/100th and 1/1000th. All right. Now, based on this table evidence, you should be able to figure out these limits in letter B. All right. So think about that for a minute. Okay. All right, let's go through each limit in letter B. Now notice what this is doing, really. It says, what is the limit as x goes to infinity of 1 divided by x? And again, the idea here is as x is growing without bound, as x is getting larger and larger, I guess it would be here, right? Then what are these y values doing? And they're headed towards 0. Likewise, when x heads towards negative infinity, right, when it grows without bound but in a negative direction, they are also the outputs headed towards 0. Look at these outputs. They're getting smaller and smaller, getting closer and closer to 0. But we can also flip that coin over, right? If I look at x going to 0, but from the right, that's in here, going towards 0, but from the right, look at these y values. They're just getting larger and larger. They're going to infinity. And likewise, if we have x headed towards 0, but from the left, those y values are getting bigger and bigger, but in a negative sense. All right? Now, this rests on a very simple principle about division. All right, make sure you understand this. If I have a numerator, if I have the top of my fraction, the numerator, and it's just a finite number divided by some quantity, let me call it x, right? As x gets bigger, the fraction gets smaller. And as x gets smaller, the fraction gets bigger. All right? And when I say smaller and bigger, I'm talking in size, not like, ooh, -10 is a really small number, because it's not, right? And it just makes sense. If I've got something and I divide it by larger and larger amounts, what I have in each amount gets smaller and smaller, right? Therefore, if the denominator goes to infinity and the numerator is a nice finite number, well, then the overall limit is going to be 0. But flip that around. If the denominator heads towards 0, then the overall fraction has to either head towards infinity or negative infinity. All right? So, very, very important, that discussion. Pause the video now, really think hard about it, make sure you get it, and then we're moving on. Okay, here we go. So, let's tackle some limits. The first type of limit that we're going to look at is the limit as x goes to either infinity or negative infinity. And these are going to be very, very easy, okay? You're going to like these because all we have to do is consider what's known as the long-run behavior of both the numerator and the denominator. Now, in Algebra 2 with Trig Honors at Arlington High School, students learn that as x gets very large, either very large positive or very large negative, the only thing that matters about a polynomial is the monomial of highest power. So in other words, because x is going to infinity, I can say that this is the same as this. These two are the same. Some teachers don't call this long-run behavior, they call it dominant term analysis. And I like that name, dominant term analysis, because when x gets even relatively large, squaring it is way, way more important than raising it to the first, or to any random constant added on. Now again, I need to emphasize, this equality is only okay because x is heading to infinity. If x was heading to 100, which is relatively large, that equality wouldn't hold. They'd give you different answers. If x was headed towards -1,000, that equality wouldn't hold. They'd give you different answers. But when x goes to infinity, the only thing that matters in the numerator is the highest power, and the only thing that matters in the denominator is the highest power. And then the beautiful thing is, I've got a monomial divided by a monomial. And at that point, these two cancel. I'm now looking at the limit as x goes to infinity of the constant 3/2, and that's 3/2. Wow, that was simple. Wow, that was easy. All right, why don't you try that dominant term analysis on letter B? See what you find there. All right, let's go through it. This one's a little bit trickier, and it does work out differently. Again, because x is going to infinity, I can just retain the 2x in the numerator and the 4x squared in the denominator. Right? And now I can simplify this. Now I have to simplify it correctly, right? It simplifies down to 1 divided by 2x. If you botch that, if you get x over 2 or 2 over x or something like that, it could give you the wrong answer. Now, think about this for a minute, right? Ultimately speaking, what happens is the numerator is a finite number, and the denominator is headed towards infinity. That means this overall limit has to head to 0, right? If I take a finite number and I divide it by infinity, it's got to head towards 0. All right, why don't you try letter C? right, let's go through it. Again, infinity, negative infinity doesn't really matter in terms of dominant term analysis. Because x is heading to negative infinity, I can take just 2x cubed in the numerator. I can just take x squared in the denominator. This gives me the limit as x goes to negative infinity of 2x. And now that is going to be negative infinity, right? And it's going to be negative infinity since I plug larger and larger negative numbers in for x, and then multiply by 2, I'm just going to get larger and larger negative numbers. So that should be relatively simple, right? If x is going to infinity or x is going to negative infinity, all you have to be concerned with are the highest power terms in the numerator and denominator. That will always result in a monomial divided by a monomial, which can be simplified into a power expression, if you will. And then you can think about what the limits are from there. All right, I'm going to clear this out, so pause the video if you need to. All right, here we go. All right, now the other types of limits that we have are limits where the output goes to infinity. These tend to be much harder for students because this is all about taking an integer, typically, doesn't have to be an integer, but taking a finite number and dividing it by something very small. So again, before we were looking at taking a finite number and dividing it by something very large. Here we're looking at taking a finite number and dividing it by very small. All right, infinitesimally small. And because we're dividing a finite number by something infinitesimally small, the result is getting infinitesimally large. It's either headed towards infinity or negative infinity. So let's take a look at these. These are directional limits. Take a look, right? The limit of x divided by 1 minus x as x goes to 1 from the right. All right, now if we just did substitution, which we do on a lot of limits, right, we would get something that looks like this. Okay? Now, a lot of students will look at that and just go, well, that doesn't exist. Now notice what it isn't. It's not 0 divided by 0. When we have 0 divided by 0, then we got the factor cancel, the rationalize, all that. Here, we've got a finite number divided by something very small. Now, I know you're saying that's not just something very small, that's 0. But we never actually hit x equals 1. So I want you to think about this, right? We're approaching 1 from the right, which means we're going through numbers like 1.5, then 1.1, then 1.01, then 1.001, etc. So it's going to boil down to this simple. Does the denominator approach 0 from the left, or does it approach it from the right? If I take any of these numbers and I substitute them into the denominator, I get like 1 minus 1.5, or 1 minus 1.1, or 1 minus 1.01, or 1 minus 1.001. Right? Positive or negative? And the answer is they're all negative. So if I really wanted to write out my work, I'd show it like this. And then I'd say a positive divided by a negative is a negative, and it's heading to infinity. So negative infinity, right? It just recognizes the fact that when I divide a non-zero number by a number approaching 0, the result has to go to infinity or negative infinity. All right, let's do letter B. This thinking can be very tricky for some students, so if you're confused, it's understandable. Now watch, I'm not going to worry about coming in from the left. If I plug this into here, I get negative 4 divided by 0, a non-zero number divided by 0. All right, but the question is it's not really 0, it's an infinitesimal quantity. Is it a negative infinitesimal or is it a positive infinitesimal? All right, so this is where I like my number line. I'm approaching negative 2 from the left, so I'm kind of coming in here, right? So I've got numbers like negative 2.5, I've got a number like negative 2.1, I've got a number like negative 2.01, etc. So if I put any of these into the denominator, will it be positive or negative? Well, they'll be negative. But yet, now I have a negative divided by a negative, which must be a positive, and it's got to go to infinity. So positive infinity in that case. That's it. That's the whole deal. They're not really that bad. The key is to really understand division by very small numbers. All right. Well, I'm going to clear this text out, write down anything you have to, and then we'll move on to do one more problem. Oop. All right. Exercise 4. Evaluate the limit of 1 divided by x minus 3 as x goes to 3. Beware. This is not a directional limit, so you must consider both the limit from x coming in from the left and the limit of x coming into 3 from the right. All right, do it. Do the analysis. Think about it. All right, let's go through it. So we'll take one of them each at a time. So I don't care. Let's do limit of 1 over x minus 3 as x goes to 3 from the left. Let's see if I substitute it in. It would be 1 divided by 0. I know something's up. To go to negative 3 from the left, I'd go through negative 2.9. Or I'm sorry, not negative 2.9, but 2.9, 2.99, etc. I'm getting closer and closer. But because I have a smaller number subtracting a larger number, I get an analysis like this. Now I have a positive divided by a negative equals a negative, and specifically negative infinity. On the other hand, if I look at the limit of 1 over x minus 3 as x goes to 3 from the right, again, that's going to be 1 divided by 0 upon substitution. But now if I take numbers like 3.5, 3.1, 3.01, etc., and I substitute them in here, I will get a plus. Oh, phone is ringing. I'm going to pause for a second, okay? All right, well, I got that phone call over with, so let's make sure that we finish this one off. I think we were at a point where we were talking about the fact that if we're coming into 3 from the right, that denominator is going to 0, but it's always going from a positive side. A positive, nope, sorry about that. Activate my pen. A positive divided by a positive will always result in a positive, and it'll be positive infinity. Now, we still haven't answered the original question, which is what is this limit? And of course, that means that the limit of 1 over x minus 3 as x goes to 3 does not exist. Right? And it doesn't exist because these numbers aren't the same. Okay? So that's always our test for a limit existing when we've dropped the little plus and the minus. If coming from both directions we're headed towards the same place, the limit exists. So if both of these headed towards infinity, we'd say that the answer was infinity. All right. Pause the video now if you need to. Then I'm going to clear out the text. All right, here we go. All right, take a look at the last one. Again, just like the last one, this is not a directional limit, which ironically means that you have to consider both directions. So why don't you do that? Pause the video and consider both directions to think about this limit. All right, let's go through it. Well, unlike the last one, this time the limit does exist. All right, and it exists for a very simple reason. In fact, it doesn't matter whether I'm going here or whether I'm going here. When I substitute in, I get 1 divided by 0 with a little plus. And the reason that I do is that I'm squaring it, right? So when I get negative 2 plus 2, or I take a number like negative 1.99 or a number like negative 2.01, and I add it to 2, right? So this is coming in from the right, coming in from the left, and I square it. Either way, I'm going to get a number very close to 0 that's positive. So in both cases, this is going to positive infinity. It doesn't matter whether I'm coming from the left or the right, and so I get positive infinity. One can understand this graphically, right? Because this function, y equals 1 divided by x plus 2 quantity squared, is simply the function y equals 1 over x squared that's been shifted 2 units to the left. So from both directions, we're headed up towards infinity. All right? So pause the video now, write down what you need to, then we'll finish up the lesson. Okay, here we go. Today's lesson on limits that involve infinity is one of the more challenging ones, because really, there's two things that happen with infinity. Either x is headed towards infinity, or negative infinity, or the output to the function is, and you treat them both very differently. When x is headed towards infinity, or negative infinity, you only pay attention to the long-run behavior of the polynomials involved, i.e. you only pay attention to the highest powered terms. On the other hand, when the function is going to infinity, that's harder to spot, but that will happen when you take a non-zero number and you divide it by a number that's getting closer and closer to 0. Then the only issue is, did it go to infinity or did it go to negative infinity? All right? Okay, for now I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking,